let's see what this looks like, eh? If we've done it all right, we should be able to pass it in a dictionary just like this and see some nice plots like this. Let's give it a go. And I'm going to call plot loss curves, and I'm going to pass in model 0 results. Alrighty then, okay, so that's not too bad. Now, why do I say that? Well, because we're looking here for mainly trends. We haven't trained our model for too long. Quantitatively, we know that our model hasn't performed at the way we'd like it to do. So we would like the accuracy on both the train and test data sets to be higher. And then of course, if the accuracy is going higher, then the loss is going to come down. So the ideal trend for a loss curve is to go down from the top left to the bottom right. In other words, the loss is going down over time. So the trend is all right here. So potentially if we train for more epochs, which I'd encourage you to give it a go, our model's loss might get lower. And the accuracy is also trending in the right way. Our accuracy, we want it to go up over time. So if we train for more epochs, these curves may continue to go on. Now, they may not. You never really know, right? You can guess these things, but until you try it, you don't really know. So in the next video, we're going to have a look at some different forms of loss curves. But before we do that, I'd encourage you to go through this guide here, Interpreting Loss Curves. So I feel like if you just search up loss curves, you're going to find Google's guide, or you could just search Interpreting Loss Curves. Because as you'll see, there's many different ways that loss curves can be interpreted. But the ideal trend is for the loss to go down over time and metrics like accuracy to go up over time. So in the next video, let's cover a few different forms of loss curves, such as the ideal loss curve, what it looks like when your model's underfitting, and what it looks like when your model's overfitting. And if you'd like to have a primer on those things, I'd read through this guide here. Don't worry too much if you're not sure what's happening. We're going to cover a bit more about loss curves in the next video. I'll see you there. In the last video, we looked at our model's loss curves and also the accuracy curves. And a loss curve is a way to evaluate a model's performance over time, such as how long it was training for. And as you'll see, if you Google some images of loss curves, you'll see many different types of loss curves. They come in all different shapes and sizes. And there's many different ways to interpret loss curves. So this is Google's testing and debugging and machine learning guide. So I'm going to set this as extra curriculum for this section. So we're up to number 8. Let's have a look at what should an ideal loss curve look like. So we'll just link that in there. Now, loss curve, I'll just rewrite here, is a loss curve is, I'll just make some space. A loss curve is one of the most helpful ways to troubleshoot a model. So the trend of a loss curve, you want it to go down over time, and the trend typically of an evaluation metric like accuracy, you want it to go up over time. So let's go into the keynote, loss curves. So a way to evaluate your model's performance over time. These are 3 of the main different forms of loss curve that you'll face, but again, there's many different types as mentioned in here, interpreting loss curves. Sometimes you get it going all over the place. Sometimes your loss will explode. Sometimes your metrics will be contradictory. Sometimes your testing loss will be higher than your training loss. We'll have a look at what that is. Sometimes your model gets stuck. In other words, the loss doesn't reduce. Let's have a look at some loss curves here in the case of underfitting, overfitting, and just right. So this is the Goldilocks zone. Underfitting is when your model's loss on the training and test data sets could be lower. So in our case, if we go back to our loss curves, of course we want this to be lower, and we want our accuracy to be higher. So from our perspective, it looks like our model is underfitting. And we would probably want to train it for longer, say 10, 20 epochs to see if this trend continues. If it keeps going down, it may stop underfitting. So underfitting is when your loss could be lower. Now, the inverse of underfitting is called overfitting. And so two of the biggest problems in machine learning is trying to reduce underfitting, so in other words, make your loss lower, and also reduce overfitting. These are both active areas of research because you always want your model to perform better, but you also want it to perform pretty much the same on the training set as it does the test set. And so overfitting would be when your training loss is lower than your testing loss. And why would this be overfitting? So it means overfitting because your model is essentially learning the training data too well. And that means the loss goes down on the training data set, which is typically a good thing. However, this learning is not reflected in the testing data set. So your model is essentially memorizing patterns in the training data set that don't generalize well to the test data set. So this is where we come to the just right curve, is that we want ideally our training loss to reduce as much as our test loss. And quite often you'll find that the loss is slightly lower on the training set than it is on the test set. And that's just because the model is exposed to the training data and it's never seen the test data before. So it might be a little bit lower on the training data set than on the test data set. So underfitting, the model's loss could be lower. Overfitting, the model is learning the training data too well. Now this would be equivalent to say you were studying for a final exam and you just memorized the course materials, the training set, and when it came time to the final exam, because you'd only memorized the course materials, you couldn't adapt those skills to questions you hadn't seen before. So the final exam would be the test set. So that's overfitting. The train loss is lower than the test loss. And just right, ideally, you probably won't see loss curves this exact smooth. I mean, they might be a little bit jumpy. Ideally, your training loss and test loss go down at a similar rate. And of course, there's more combinations of these. If you'd like to see them, check out the Google's loss curve guide that you can check that up there. That's some extra curriculum. Now, you probably want to know, how do you deal with underfitting and overfitting? Let's look at a few ways. We'll start with overfitting. So we want to reduce overfitting. In other words, we want our model to perform just as well on the training data set as it does on the test data set. So one of the best ways to reduce overfitting is to get more data. So this means that our training data set will be larger, our model will be exposed to more examples, and will thus, in theory, it doesn't always work. These all come with a caveat, right? They don't always work, as with many things in machine learning. So get more data. Give your model more chance to learn patterns, generalizable patterns in a data set. You can use data augmentation, so make your model's training data set harder to learn. So we've seen a few examples of data augmentation. You can get better data. So not only more data, perhaps the data that you're using isn't that, the quality isn't that good. So if you enhance the quality of your data set, your model may be able to learn better, more generalizable patterns and in turn reduce overfitting. Use transfer learning. So we're going to cover this in a later section of the course, but transfer learning is taking one model's that works, taking its patterns that it's learned and applying it to your own data set. So for example, I'll just go into the Torch Vision models library. Many of these models in here, in Torch Vision, the models module, have already been trained on a certain data set, and such as ImageNet, and you can take the weights or the patterns that these models have learned, and if they work well on an ImageNet data set, which is millions of different images, you can adjust those patterns to your own problem. And oftentimes that will help with overfitting. If you're still overfitting, you can try to simplify your model. Usually this means taking away things like extra layers, taking away more hidden units. So say you had 10 layers, you might reduce it to 5 layers. Why does this, what's the theory behind this? Well, if you simplify your model and take away complexity from your model, you're kind of telling your model, hey, use what you've got, and you're going to have to, because you've only got 5 layers now, you're going to have to make sure that those 5 layers work really well because you've no longer got 10. And the same for hidden units. Say you started with 100 hidden units per layer, you might reduce that to 50 and say, hey, you had 100 before, now use those 50 and make your patterns generalizable. Use learning rate decay. So the learning rate is how much your optimizer updates your model's weights every step. So learning rate decay is to decay the learning rate over time. So you might look this up. You can look this up, go PyTorch learning rate scheduling. So what this means is you want to decrease your learning rate over time. Now, I know I'm giving you a lot of different things here, but you've got this keynote as a reference, so you can come across these over time. So learning rate scheduling. So we might look into here. Do we have schedule? Scheduler. Beautiful. So this is going to adjust the learning rate over time. So for example, at the start of when a model is training, you might want a higher learning rate. And then as the model starts to learn patterns more and more and more, you might want to reduce that learning rate over time so that your model doesn't update its patterns too much in later epochs. So that's the concept of learning rate scheduling. The closer you get to convergence, the lower you might want to set your learning rate. Think of it like this. If you're reaching for a coin at the back of a couch, can we get an image of that? Coin at back of couch. Images. So if you're trying to reach a coin in the cushions here, so the closer you get to that coin, at the beginning you might take big steps, but then the closer you get to that coin, the smaller the step you might take to pick that coin out. Because if you take a big step when you're really close to the coin here, the coin might fall down the couch. The same thing with learning rate decay. At the start of your model training, you might take bigger steps as your model works its way down the loss curve. But then you get closer and closer to the ideal position on the loss curve. You might start to lower and lower that learning rate until you get right very close to the end and you can pick up the coin. Or in other words, your model can converge. And then finally, use early stopping. So if we go into an image, is there early stopping here? Early stopping. Loss curves, early stopping. So what this means is that you stop. Yeah, there we go. So there's heaps of different guides. Early stopping with PyTorch, beautiful. So what this means is before your testing error starts to go up, you keep track of your model's testing error, and then you stop your model from training, or you save the weights, or you save the patterns where your model's loss was the lowest. So then you could just set your model to train for an infinite amount of training steps. And as soon as the testing error starts to increase for, say, 10 steps in a row, you go back to this point here and you go, I think that was where our model was the best, and the testing error started to increase after that, so we're going to save that model there instead of the model here. So that's the concept of early stopping. So that's dealing with overfitting. There are other methods to deal with underfitting. So recall, underfitting is when we have a loss that isn't as low as we'd like it to be. Our model is not fitting the data very well, so it's underfitting. So to reduce underfitting, you can add more layers/units to your model. You're trying to increase your model's ability to learn by adding more layers or units. You can again tweak the learning rate. Perhaps your learning rate is too high to begin with and your model doesn't learn very well. So you can adjust the learning rate again, just like we discussed with reaching for that coin at the back of a couch. If your model is still underfitting, you can train for longer. So that means giving your model more opportunities to look at the data. So more epochs, that just means it's got looking at the training set over and over and over and over again and trying to learn those patterns. However, you might find again, if you try to train for too long, your testing error will start to go up. Your model might start overfitting if you train too long. So machine learning is all about a balance between underfitting and overfitting. You want your model to fit quite well. And so this is a great one. So you want your model to start fitting quite well, but then if you try to reduce underfitting too much, you might start to overfit, and then vice versa, right? If you try to reduce overfitting too much, your model might underfit. So this is one of the most fun dances in machine learning, the balance between overfitting and underfitting. Finally, you might use transfer learning. So transfer learning helps with overfitting and underfitting. Recall, transfer learning is using a model's learned patterns from one problem and adjusting them to your own. We're going to see this later on in the course. And then finally, use less regularization. So regularization is holding your model back. So it's trying to prevent overfitting. So if you do too much preventing of overfitting, in other words, regularizing your model, you might end up underfitting. So if we go back, we have a look at the ideal curves. Underfitting, if you try to prevent underfitting too much, so increasing your model's capability to learn, you might end up overfitting. And if you try to prevent overfitting too much, you might end up underfitting. We are going for the just right section. And this is going to be a balance between these two throughout your entire machine learning career. In fact, it's probably the most prevalent area of research is trying to get models not to underfit, but also not to overfit. So keep that in mind. A loss curve is a great way to evaluate your model's performance over time. And a lot of what we do with the loss curves is try to work out whether our model is underfitting or overfitting, and we're trying to get to this just right curve. We might not get exactly there, but we want to keep trying getting as close as we can. So with that being said, let's now build another model in the next video, and we're going to try a method to try and see if we can use data augmentation to prevent our model from overfitting. Although that experiment doesn't sound like the most ideal one we could do right now, because it looks like our model is underfitting. So with your knowledge of what you've just learned in the previous video, how to prevent underfitting, what would you do to increase this model's capability of learning patterns in the training data set? Would you train it for longer? Would you add more layers? Would you add more hidden units? Have a think, and we'll start building another model in the next video. Welcome back. In the last video, we covered the important concept of a loss curve and how it can give us information about whether our model is underfitting. In other words, our model's loss could be lower, or whether it's overfitting. In other words, the training loss is lower than the test loss, or far lower than the validation loss. That's another thing to note here, is that I've put training and test sets here. You could also do this with a validation data set. And that the just right, the Goldilocks zone, is when our training and test loss are quite similar over time. Now, there was a fair bit of information in that last video, so just wanted to highlight that you can get this all in section 04, which is the notebook that we're working on. And then if you come down over here, if we come to section 8, what should an ideal loss curve look like? We've got underfitting, overfitting, just right, how to deal with overfitting. We've got a few options here. We've got how to deal with underfitting, and then we've got a few options there. And then if we wanted to look for more, how to deal with overfitting. You could find a bunch of resources here, and then how to deal with underfitting. You could find a bunch of resources here as well. So that is a very fine line, very fine balance that you're going to experience throughout all of your machine learning career. But it's time now to move on. We're going to move on to creating another model, which is TinyVGG with data augmentation this time. So if we go back to the slide, data augmentation is one way of dealing with overfitting. Now, it's probably not the most ideal experiment that we could take because our model 0, our baseline model, looks like it's underfitting. But data augmentation, as we've seen before, is a way of manipulating images to artificially increase the diversity of your training data set without collecting more data. So we could take our photos of pizza, sushi, and steak and randomly rotate them 30 degrees. And increased diversity forces a model to learn, or hopefully learn. Again, all of these come with a caveat of not always being the silver bullet, to learn more generalizable patterns. Now, I should have spelled generalizable here rather than generalization, but similar thing. Let's go here. Let's create, to start off with, we'll just write down. Now let's try another modeling experiment. So this is in line with our PyTorch workflow, trying a model, then trying another one, and trying another one, so and so over again. This time using the same model as before, but with some slight data augmentation. Oh, maybe we want not slight, that's probably not the best word. We'll just say with some data augmentation. And if we come down here, we're gonna write section 9.1. We need to first create a transform with data augmentation. So we've seen what this looks like before. We're going to use the trivial augment data augmentation, create training transform, which is, as we saw in a previous video, what the PyTorch team have recently used to train their state-of-the-art computer vision models. So train transform trivial. This is what I'm going to call my transform. And I'm just going to, from Torch Vision, import transforms. We've done this before. We don't have to re-import it, but I'm going to do it anyway just to show you that we're re-importing, or we're using transforms. And we're going to compose a transform here. Recall that transforms help us manipulate our data. So we're going to transform our images into size 64 by 64. Then we're going to set up a trivial augment transforms, just like we did before. Trivial augment wide. And we're going to set the number of magnitude bins here to be 31, which is the default here, which means we'll randomly use some data augmentation on each one of our images, and it will be applied at a magnitude of 0 to 31, also randomly selected. So if we lowered this to 5, the upper bound of intensity of how much that data augmentation is applied to a certain image will be less than if we set it to, say, 31. Now, our final transform here is going to be 2 tensor because we want our images in tensor format for our model. And then I'm going to create a test transform. I'm going to call this simple, which is just going to be transforms.compose. And all that it's going to have, oh, I should put a list here. All that it's going to have, I'll just make some space over here, is going to be transforms. All we want to do is resize the image. Size equals 64, 64. Now, we don't apply data augmentation to the test data set because we only just want to evaluate our models on the test data set. Our models aren't going to be learning any generalizable patterns on the test data set, which is why we focus our data augmentations on the training data set. And I've just readjusted that. I don't want to do that. Beautiful. So we've got a transform ready. Now let's load some data using those transforms. So we'll create train and test data sets and data loaders with data augmentation. So we've done this before. You might want to try it out on your own. So pause the video if you'd like to test it out. Create a data set and a data loader using these transforms here. And recall that our data set is going to be creating a data set from pizza, steak, and sushi for the train and test folders. And that our data loader is going to be batchifying our data set. So let's turn our image folders into data sets. Data sets, beautiful. And I'm going to write here train data augmented, just so we know that it's been augmented. We've got a few of similar variable names throughout this notebook, so I just want to be as clear as possible. And I'm going to use, I'll just re-import Torch Vision data sets. We've seen this before, the image folder. So rather than use our own custom class, we're going to use the existing image folder class that's within Torch Vision datasets. And we have to pass in here a root. So I'll just get the doc string there. Root, which is going to be equal to our train dir, which recall is the path to our training directory. I've got that saved. And then I'm going to pass in here, the transform is going to be train transform trivial. So our training data is going to be augmented thanks to this transform here, and transforms trivial augment wide. You know where you can find more about trivial augment wide, of course, in the PyTorch documentation, or just searching transforms trivial augment wide. And did I spell this wrong? Trivial. Oh, train transform. I spelled that wrong. Of course I did. So test data, let's create this as test data simple equals datasets dot image folder. And the root dir is going to be here, the test directory. And the transform is just going to be what? The test transform simple. Beautiful. So now let's turn these data sets into data loaders. So turn our data sets into data loaders. We're going to import OS. I'm going to set the batch size here to equal to 32. The number of workers that are going to load our data loaders, I'm going to set this to os.cpu count. So there'll be one worker per CPU on our machine. I'm going to set here the torch manual seed to 42 because we're going to shuffle our training data. Train data loader, I'm going to call this augmented, equals data loader. Now I don't need to re-import this, but I just want to show you again. From torch.utils, you can never have enough practice, right? .data, let's import data loader. So that's where we got the data loader class from. Now let's go train data augmented. We'll pass in that as the data set. And I'll just put in here the parameter name for completeness. That's our data set. And then we want to set the batch size, which is equal to batch size. I'm going to set shuffle equal to true, and I'm going to set num workers equal to num workers. Beautiful. And now let's do that again with the test data loader this time. Test data loader, I'm going to call this test data loader simple. We're not using any data augmentation on the test data set, just turning our images, our test images, into tensors. The data set here is going to be test data simple. I'm going to pass in the batch size equal to batch size, so both our data loaders will have a batch size of 32. I'm going to keep shuffle on false, and num workers I'm going to set to num workers. Look at us go. We've already got a data set and a data loader. This time our data loader is going to be augmented for the training data set, and it's going to be nice and simple for the test data set. So this is really similar, this data loader, to the previous one we made. The only difference in this modeling experiment is that we're going to be adding data augmentation, namely trivial augment wide. So with that being said, we've got a data set, we've got a data loader. In the next video, let's construct and train model 1. In fact, you might want to give that a go. So you can use our tinyVGG class to make model 1, and then you can use our train function to train a new tinyVGG instance with our training data loader augmented and our test data loader simple. So give that a go, and we'll do it together in the next video. I'll see you there. Now that we've got our data sets and data loaders with data augmentation ready, let's now create another model. So 9.3, we're going to construct and train model 1. And this time, I'm just going to write what we're going to be doing. This time we'll be using the same model architecture, but we're changing the data here. Except this time we've augmented the training data. So we'd like to see how this performs compared to a model with no data augmentation. So that was our baseline up here. And that's what you'll generally do with your experiments. You'll start as simple as possible and introduce complexity when required. So create model 1 and send it to the target device, that is, to the target device. And because of our helpful selves previously, we can create a manual seed here, torch.manual seed, and we can create model 1 leveraging the class that we created before. So although we built tinyVGG from scratch in this video, in this section, in subsequent coding sessions, because we've built it from scratch once and we know that it works, we can just recreate it by calling the class and passing in different variables here. So let's get the number of classes that we have in our train data augmented classes, and we're going to send it to device. And then if we inspect model 1, let's have a look. Wonderful. Now let's keep going. We can also leverage our training function that we did. You might have tried this before. So let's now train our model. I'm just going to put here, wonderful. Now we've got a model and data loaders. Let's create, what do we have to do? We have to create a loss function and an optimizer and call upon our train function that we created earlier. to train and evaluate our model. Beautiful. So I'm going to set the random seeds, torch.manual seeds, and torch.CUDA, because we're going to be using CUDA. Let's set the manual seed here, 42. I'm going to set the number of epochs. We're going to keep many of the parameters the same. Set the number of epochs, num epochs equals 5. We could, of course, train this model for longer if we really wanted to by increasing the number of epochs. But now let's set up the loss function. So loss fn equals nn cross entropy loss. Don't forget, this just came into mind. Loss function often as well in PyTorch is called criterion. So the criterion you're trying to reduce, but I just like to call it loss function. And then we're going to have optimizer. Let's use the same optimizer we used before, torch.optim.atom. Recall, SGD and atom are two of the most popular optimizers. So model1.parameters, they're the parameters we're going to optimize. We're going to set the learning rate to 001, which is the default for the atom optimizer in PyTorch. Then we're going to start the timer. So from timeIt, let's import the default timer as timer. And we'll go start time equals timer. And then let's go train model 1. How can we do this? Well, we're going to get a results dictionary as model 1 results. We're going to call upon our train function. Inside our train function, we'll pass the model parameter as model 1. For the train data loader parameter, we're going to pass in train data loader augmented, so our augmented training data loader. And for the test data loader, we can pass in here test data loader simple. And then we can write our optimizer, which will be the atom optimizer. Our loss function is going to be nn cross entropy loss, what we've created above. And then we can set the number of epochs is going to be equal to num epochs. And then if we really wanted to, we could set the device equal to device, which will be our target device. And now let's end the timer and print out how long it took. End time equals timer, and we'll go print total training time for model 1 is going to be end time minus start time, and it would help if I could spell. We'll get that to 3 decimal places, and that'll be seconds. So you're ready? Look how quickly we built a training pipeline for model 1. And look how easily we created it. So go us for coding all of that stuff up before. Let's train our second model. Our first model using data augmentation. You ready? 3, 2, 1, let's go. No errors. Beautiful. We're going nice and quick here. So, about just over 7 seconds. So what GPU do I have currently? Just keep this in mind that I'm using Google Colab Pro, so I get preference in terms of allocating a faster GPU. Your model training time may be longer than what I've got, depending on the GPU. It also may be faster, again, depending on the GPU. But we get about 7 seconds, but it looks like our model with data augmentation didn't perform as well as our model without data augmentation. So how long did our model before without data augmentation take to train? Just over 7 seconds as well. But we got better results in terms of accuracy on the training and test data sets for model 0. So maybe data augmentation doesn't help in our case. And we kind of hinted at that because the loss here was already going down. We weren't really overfitting yet. So recall that data augmentation is a way to help with overfitting generally. So maybe that wasn't the best step to try and improve our model. But let's nonetheless keep evaluating our model. In the next video, we're going to plot the loss curves of model 1. So in fact, you might want to give that a go. So we've got a function, plot loss curves, and we've got some results in a dictionary format. So try that out, plot the loss curves, and see what you see. Let's do it together in the next video. I'll see you there. In the last video, we did the really exciting thing of training our first model with data augmentation, but we also saw that quantitatively, it looks like that it didn't give us much improvement. So let's keep evaluating our model here. I'm going to make a section. Recall that one of my favorite ways, or one of the best ways, not just my favorite, to evaluate the performance of a model over time is to plot the loss curves. So a loss curve helps you evaluate your model's performance over time. And it will also give you a great visual representation or a visual way to see if your model is underfitting or overfitting. So let's plot the loss curves of Model 1 results and see what happens. We're using this function we created before. And oh my goodness, is that going in the right direction? It looks like our test loss is going up here. Now, is that where we want it to go? Remember, the ideal direction for a loss curve is to go down over time because loss is measuring what? It's measuring how wrong our model is. And the accuracy curve looks like it's all over the place as well. I mean, it's going up kind of, but maybe we don't have enough time to measure these things. So an experiment that you could do is train both of our models, Model 0 and Model 1, for more epochs and see if these loss curves flatten out. So I'll pose you the question, is our model underfitting or overfitting right now? Or both? So if we want to have a look at the loss curves, our just right is for the loss, that is, this is not for accuracy, this is for loss. Over time, we want it to go down. So for me, our model is underfitting because our loss could be lower, but it also looks like it's overfitting as well. So it's not doing a very good job because our test loss is far higher than our training loss. So if we go back to section 4 of the Learn pytorch.io book, what should an ideal loss curve look like? I'd like you to start thinking of some ways that we could deal with overfitting of our model. So could we get more data? Could we simplify it? Could we use transfer learning? We're going to see that later on, but you might want to jump ahead and have a look. And if we're dealing with underfitting, what are some other things that we could try with our model? Could we add some more layers, potentially another convolutional block? Could we increase the number of hidden units per layer? So if we've got currently 10 hidden units per layer, maybe you want to increase that to 64 or something like that. Could we train it for longer? That's probably one of the easiest things to try with our current training functions. We could train for 20 epochs. So have a go at this, reference this, try out some experiments with, see if you can get these loss curves more towards the ideal shape. And in the next video, we're going to keep pushing forward. We're going to compare our model results. So we've done 2 experiments. Let's now see them side by side. We've looked at our model results individually, and we know that they could be improved. But a good way to compare all of your experiments is to compare your model's results side by side. So that's what we're going to do in the next video. I'll see you there. Now that we've compared our model's loss curves on their own individually, how about we compare our model results to each other? So let's have a look at comparing our model results. And so I'm going to write a little note here that after evaluating our modeling experiments on their own, it's important to compare them to each other. And there's a few different ways to do this. Number 1 is hard coding. So like we've done, we've written functions, we've written helper functions and whatnot, and manually plotted things. So I'm just going to write in here, this is what we're doing. Then of course there are tools to do this, such as PyTorch plus TensorBoard. And so I'll link to this, PyTorch TensorBoard. We're going to see this in a later section of the course. TensorBoard is a great resource for tracking your experiments. If you'd like to jump forward and have a look at what that is in the PyTorch documentation, I'd encourage you to do so. Then another one of my favorite tools is weights and biases. So these are all going to involve some code as well, but they help out with automatically tracking different experiments. So weights and biases is one of my favorite, and you've got platform for experiments. That's what you'll be looking at. So if you run multiple experiments, you can set up weights and biases pretty easy to track your different model hyperparameters So PyTorch, there we go. Import weights and biases, start a new run on weights and biases. You can save the learning rate value and whatnot, go through your data and just log everything there. So this is not a course about different tools. We're going to focus on just pure PyTorch, but I thought I'd leave these here anyway because you're going to come across them eventually. And ML Flow is another one of my favorites as well. We have ML tracking, projects, models, registry, all that sort of stuff. If you'd like to look into more ways to track your experiments, there are some extensions. But for now, we're going to stick with hard coding. We're just going to do it as simple as possible to begin with. And if we wanted to add other tools later on, we can sure do that. So let's create a data frame for each of our model results. We can do this because our model results, recall, are in the form of dictionaries. So model 0 results. But you can see what we're doing now by hard coding this, it's quite cumbersome. Can you imagine if we had, say, 10 models or even just 5 models? We'd have to really write a fair bit of code here for all of our dictionaries and whatnot, whereas these tools here help you to track everything automatically. So we've got a data frame here. Model 0 results over time. These are our number of epochs. We can notice that the training loss starts to go down. The testing loss also starts to go down. And the accuracy on the training and test data set starts to go up. Now, those are the trends that we're looking for. So an experiment you could try would be to train this model 0 for longer to see if it improved. But we're currently just interested in comparing results. So let's set up a plot. I want to plot model 0 results and model 1 results on the same plot. So we'll need a plot for training loss, we'll need a plot for training accuracy, test loss, and test accuracy, and then we want 2 separate lines on each of them, one for model 0 and one for model 1. And this particular pattern would be similar regardless if we had 10 different experiments or if we had 10 different metrics we wanted to compare. You generally want to plot them all against each other to make them visual. And that's what tools such as weights and biases, what TensorBoard, and what ML Flow can help you to do. So I'm just going to get out of that, clean up our browser. So let's set up a plot here. I'm going to use matplotlib, going to put in a figure. I'm going to make it quite large because we want 4 subplots, one for each of the metrics we want to compare across our different models. Now let's get number of epochs. So epochs is going to be length, or we'll turn it into a range actually. Range of len model 0 df, so that's going to give us 5. Beautiful, range between 0 and 5. Now let's create a plot for the train loss. We want to compare the train loss across model 0 and the train loss across model 1. So we can go plt.subplot. Let's create a plot with 2 rows and 2 columns, and this is going to be index number 1 will be the training loss. We'll go plt.plot. I'm going to put in here epochs and then model 0 df. Inside here, I'm going to put train loss for our first metric, and then I'm going to label it with model 0. So we're comparing the train loss on each of our modeling experiments. Recall that model 0 was our baseline model, and that was tinyVGG without data augmentation. And then we tried out model 1, which was the same model, but all we did was we added a data augmentation transform to our training data. So PLT, and we'll go X label, they both used the same test data set. And PLT.legend. Let's see what this looks like. Wonderful. So there's our training loss across 2 different models. So we notice that model 0 is trending in the right way. Model 1 kind of exploded on epoch number, that would be 0, 1, 2, or 1, depending how you're counting. Let's just say epoch number 2, because that's easier. The loss went up, but then it started to go back down. So again, if we continued training these models, we might notice that the overall trend of the loss is going down on the training data set, which is exactly what we'd like. So let's now plot, we'll go the test loss. So I'm going to go test loss here, and then I'm going to change this. I believe if I hold Control or Command maybe, nope, or Option on my Mac keyboard. Yeah, so it might be a different key on Windows, but for me I can press Option and I can get a multi-cursor here. So I'm just going to come back in here, and that way I can backspace there and just turn this into test loss. Wonderful. So I'm going to put this as test loss as the title, and I need to change the index. So this will be index 1, index 2, index 3, index 4. Let's see what this looks like. Do we get the test loss? Beautiful, that's what we get. However, we notice that model 1 is probably overfitting at this stage, so maybe the data augmentation wasn't the best change to make to our model. Recall that even if you make a change to your model, such as preventing overfitting or underfitting, it won't always guarantee that the change takes your model's evaluation metrics in the right direction. Ideally, loss is going from top left to bottom right over time. So looks like model 0 is winning out here at the moment on the loss front. So now let's plot the accuracy for both training and test. So I'm going to change this to train. I'm going to put this as accuracy. And this is going to be index number 3 on the plot. And do we save it as, yeah, just AC. Wonderful. So I'm going to option click here on my Mac. This is going to be train, and this is going to be accuracy here. And then I'll change this one to accuracy. And then I'm going to change this to accuracy. And this is going to be plot number 4, 2 rows, 2 columns, index number 4. And I'm going to option click here to have 2 cursors, test AC, and then I'll change this to test AC. And I'm going to get rid of the legend here. It takes a little bit to plot because we're doing 4 graphs in one hit. Wonderful. So that's comparing our models, but do you see how we could potentially functionize this to plot however many model results that we have? But if we had, say, another 5 models, we did another 5 experiments, which is actually not too many experiments on a problem. You might find that sometimes you do over a dozen experiments for a single modeling problem, maybe even more. These graphs can get pretty outlandish with all of the lines going through. So that's again what tools like TensorBoard, weights and biases, and MLflow will help with. But if we have a look at the accuracy, it seems that both of our models are heading in the right direction. We want to go from the bottom left up in the case of accuracy. But the test accuracy, that's training. Oh, excuse me. Is this not training accuracy? I messed up that. Did you catch that one? So training accuracy, we're heading in the right direction, but it looks like model 1 is, still overfitting. So the results we're getting on the training data set aren't coming over to the testing data set. And that's what we really want our models to shine, is on the test data set. So metrics on the training data set are good, but ideally we want our models to perform well on the test data set, data it hasn't seen before. So that's just something to keep in mind. Whenever you do a series of modeling experiments, it's always good to not only evaluate them individually, evaluate them against each other. So that way you can go back through your experiments, see what worked and what didn't. If you were to ask me what I would do for both of these models, I would probably train them for longer and maybe add some more hidden units to each of the layers and see where the results go from there. So give that a shot. In the next video, let's see how we can use our trained models to make a prediction on our own custom image of food. So yes, we used a custom data set of pizza, steak, and sushi images, but what if we had our own, what if we finished this model training and we decided, you know what, this is a good enough model, and then we deployed it to an app like Nutrify.app, which is a food recognition app that I'm personally working on. Then we wanted to upload an image and have it be classified by our PyTorch model. So let's give that a shot, see how we can use our trained model to predict on an image that's not in our training data and not in our testing data. I'll see you in the next video. Welcome back. In the last video, we compared our modeling experiments. Now we're going to move on to one of the most exciting parts of deep learning, and that is making a prediction on a custom image. So although we've trained a model on custom data, how do you make a prediction on a sample / image in our case that's not in either the training or testing data set? So let's say you are building a food recognition app such as Nutrify, take a photo of food and learn about it. And you wanted to use computer vision to essentially turn foods into QR codes. So I'll just show you the workflow here. If we were to upload this image of my dad giving 2 thumbs up for a delicious pizza, and what is Nutrify predicted as? Pizza. Beautiful. So macronutrients, there you get some nutrition information and then the time taken. So we could replicate a similar process to this using our trained PyTorch model, albeit it's not going to be too great of results or performance because we've seen that we could improve our models based on the accuracy here and based on the loss and whatnot. But let's just see what it's like, the workflow. So the first thing we're going to do is get a custom image. Now we could upload one here, such as clicking the upload button in Google Colab, choosing an image, and then importing it like that. But I'm going to do so programmatically, as you've seen before. So let's write some code in this video to download a custom image. I'm going to do so using requests. And like all good cooking shows, I've prepared a custom image for us. So custom image path, but again, you could use this process that we're going to go through with any of your own images of pizza, steak, or sushi. And if you wanted to train your own model on another set of custom data, the workflow will be quite similar. So I'm going to download a photo called Pizza Dad, which is of my dad, 2 big thumbs up. And so I'm going to download it from GitHub. So this image is on the course GitHub. And let's write some code to download the image if it doesn't already exist in our Colab instance. So if you wanted to upload a single image, you could click with this button. Just beware that like all of our other data, it's going to disappear if Colab disconnects. So that's why I like to write code so we don't have to re-upload it every time. So if not custom image path.is file, let's open a request here or open a file. Going to open up the custom image path with write binary permissions as F, short for file. And then when downloading, this is because our image is stored on GitHub. When downloading an image or when downloading from GitHub in general, you typically want the raw link, need to use the raw file link. So let's write a request here equals request.get. So if we go to the PyTorch deep learning repo, then if we go into, I believe it might be extras, not in extras, it's going to be in images. That would make a lot more sense, wouldn't it, Daniel? Let's get O4 Pizza Dad. So if we have a look, this is PyTorch deep learning, images, O4 Pizza Dad. There's a big version of the image there. And then if we click download, is this going to give us the raw link? Yeah, there we go. So that's the image. Hey Dad, how you doing? Is that pizza delicious? It looks like it. Let's see if our model can get this right. What do you think? Will it? So of course we want our model to predict pizza for this image because it's got a pizza in it. So custom image path, we're going to download that. I've just put in the raw URL above. So notice the raw GitHub user content. That's from the course GitHub. Then I'm going to go f.write. So file, write the request content. So the content from the request, in other words, the raw file from GitHub here. Similar workflow for if you were getting another image from somewhere else on the internet. And else, if it is already downloaded, let's just not download it. So print f custom image path already exists, skipping download. And let's see if this works. We'll run the code. So downloading data 04pizzadad.jpg. And if we go into here, we refresh. There we go. Beautiful. So our data, or our custom image, is now in our data folder. So if we click on this, this is inside Google Colab now. Beautiful. We got a big, nice big image there. And there's a nice big pizza there. So we're going to be writing some code over the next few videos to do the exact same process as what we've been doing to import our custom data set. For our custom image, what do we still have to do? We still have to turn it into tensors, and then we have to pass it through our model. So let's see what that looks like over the next few videos. Woohoo! We are up to one of the most exciting parts of building deep learning models. and that is predicting on custom data. In our case, a custom image of a photo of my dad eating pizza. So of course, we're training a computer vision model on here on pizza, steak, and sushi. So hopefully the ideal result for our model to predict on this image will be pizza. So let's keep going. Let's figure out how we can get our image, our custom image, our singular image into tensor form. Loading in a custom image with PyTorch, creating another section here. So I'm just going to write down here, we have to make sure our custom image is in the same format as the data our model was trained on. So namely, that was in tensor form with data type torch float32 and then of shape 64 by 64 by 3. So we might need to change the shape of our image, and then we need to make sure that it's on the right device. Command MM, beautiful. So let's see what this looks like, hey? So if I'm going to import Torch Vision, now the package you use to load your data will depend on the domain you're in. So let's open up the Torch Vision documentation. We can go to models, that's okay. So if we're working with text, you might want to look in here for some input and output functions, so some loading functions. Torch Audio, same thing. Torch Vision is what we're working with. Let's click into Torch Vision. Now we want to look into reading and writing images and videos because we want to read in an image, right? We've got a custom image, we want to read it in. So this is part of your extracurricular, by the way, to go through these for at least 10 minutes each. So spend an hour if you're going through Torch Vision. You could do the same across these other ones. It will just really help you familiarize yourself with all the functions of PyTorch domain libraries. So we want to look, here's some options for video. We're not working with video. Here's some options for images. Now, what do we want to do? We want to read in an image. So we've got a few things here. Decode image. Oh, I've skipped over one. We can write a JPEG if we wanted to. We can encode a PNG. Let's jump into this one. Read image. What does it do? Reads a JPEG or PNG into a three-dimensional RGB or grayscale tensor. That is what we want. And then optionally converts the image to the desired format. The values of the output tensor are uint8. Okay, beautiful. So let's see what this looks like, eh? Mode, the read mode used optionally for converting the image. Let's see what we can do with this. I'm going to copy this in. So I'll write this down. We can read an image into PyTorch using, we'll go with that. So let's see what this looks like in practice. Read in custom image. I can't explain to you how much I love using deep learning models to predict on custom data. So custom image, we're going to call it uint8 because as we read from the documentation here, it reads it in uint8 format. So let's have a look at what that looks like rather than just talking about it. Torchvision.io, read image. What's our target image path? Well, we've got custom image path up here. This is why I like to do things programmatically. So if our Colab notebook reset, we could just run this cell again, get our custom image, and then we've got it here. So custom image uint8. Let's see what this looks like. Oh, what did we get wrong? Unable to cast Python instance. Oh, does it need to be a string? Expected a value type of string. Oh, but found POSIX path. So the path needs to be a string. Okay. If we have a look at our custom image path, what did we get wrong? Oh, we've got a POSIX path. So let's convert this custom image path into a string and see what happens. Look at that. That's how image in integer form. I wonder if this is plottable. Let's go plt.imshow custom image uint8. Maybe we get a dimensionality problem here. Invalid shape. Okay, let's permute it. Permute, and we'll go 1, 2, 0. Is this going to plot? It's a fairly big image. There we go, 2 thumbs up. Haha, look at us. So that is the power of torchvision.io. IO stands for input output. We were just able to read in our custom image. Now, how about we get some metadata about this? Let's go, we'll print it up here actually. I'll keep that there because that's fun to plot it. Let's find the shape of our data, the data type, and yeah, we've got it in tensor format, but it's uint8 right now. So we might have to convert that to float32. We want to find out its shape, and we need to make sure that if we're predicting on a custom image, the data that we're predicting on, the custom image, needs to be on the same device as our model. So let's print out some info. Print, let's go custom image tensor, and this is going to be a new line, and then we will go custom image uint8. Wonderful. And then let's go custom image shape. We will get the shape parameter, custom image shape, or attribute, sorry. And then we also want to know the data type, custom image data type, but we have a kind of an inkling because the documentation said it would be uint8, uint8, and we'll go dtype. Let's have a look. What do we have? So there's our image tensor, and it's quite a big image, so custom image shape. So what was our model trained on? Our model was trained on images of 64 by 64. So this image encodes a lot more information than what our model was trained on. So we're going to have to change that shape to pass it through our model. And then we've got an image data type here, or tensor data type of torch uint8. So maybe that's going to be some errors for us later on. So if you want to go ahead and see if you can resize this tensor to 64, 64 using a torch transform or torch vision transform, I'd encourage you to try that out. And if you know how to change a torch tensor from uint8 to torch float32, give that a shot as well. So let's try and make a prediction on our image in the next video. I'll see you there. In the last video, we loaded in our own custom image and got 2 big thumbs up from my dad, and we turned it into a tensor. So we've got a custom image tensor here. It's quite big though, and we looked at a few things of what we have to do before we pass it through our model. So we need to make sure it's in the data type torch float32, shape 64, 64.3, and on the right device. So let's make another section here. We'll go 11.2, and we'll call it making a prediction on a custom image with a PyTorch model, or with a trained PyTorch model. And albeit our models aren't quite the level we would like them at yet, I think it's important just to see what it's like to make a prediction end-to-end on some custom data. Because that's the fun part, right? So try to make a prediction on an image. Now, I want to just highlight something about the importance of different data types and shapes and whatnot, and devices. 3 of the biggest errors in deep learning. Let's see what happens if we try to predict on uint8 format. So we'll go model1.eval, and with torch.inference mode, let's make a prediction. We'll pass it through our model 1. We could use model 0 if we wanted to here. They're both performing pretty poorly anyway. Let's send it to the device and see what happens. Oh no, what did we get wrong here? Runtime error, input type. So we've got uint8. So this is one of our first errors that we talked about. We need to make sure that our custom data is of the same data type that our model was originally trained on. So we've got torch CUDA float tensor. So we've got an issue here. We've got a uint8 image data or image tensor trying to be predicted on by a model with its data type of torch CUDA float tensor. So let's try fix this by load in the custom image and convert to torch.float32. So one of the ways we can do this is we'll just recreate the custom image tensor, and I'm going to use torchvision.io.readImage. We don't have to fully reload our image, but I'm going to do it anyway for completeness and a little bit of practice. And then I'm going to set the type here with the type method to torchFloat32. And then let's just see what happens. We'll go custom image. Let's see what this looks like. I wonder if our model will work on this. Let's just try again. We'll bring this up, copy this down to make a prediction, and custom image.toDevice. Our image is in torchFloat32 now. Let's see what happens. Oh, we get an issue. Oh my goodness, that's a big matrix. Now, I have a feeling that that might be because our image, our custom image, is of a shape that's far too large. Custom image dot shape. What do we get? Oh my gosh, 4,000 and 3,024. And do you notice as well that our values here aren't between 0 and 1? Whereas our previous images, do we have an image? There we go. That our model was trained on were between 0 and 1. So how could we get these values to be between 0 and 1? Well, one of the ways to do so is by dividing by 255. Now, why would we divide by 255? Well, because that's a standard image format, is to store the image tensor values in values from 0 to 255 for red, green, and blue color channels. So if we want to scale them, so this is what I meant by 0 to 255, if we wanted to scale these values to be between 0 and 1, we can divide them by 255 because that is the maximum value that they can be. So let's see what happens if we do that. Okay, we get our image values between 0 and 1. Can we plot this image? So plt.imshow, let's plot our custom image. We got to permute it so it works nicely with matplotlib. What do we get here? Beautiful, we get the same image, right? But it's still quite big. Look at that. We've got a pixel height of, or image height of almost 4,000 pixels and a width of over 3,000 pixels. So we need to do some adjustments further on. So let's keep going. We've got custom image to device. We've got an error here. So this is a shape error. So what can we do to transform our image shape? And you might have already tried this. Well, let's create a transform pipeline to transform our image shape. So create transform pipeline or composition to resize the image. Because remember, what are we trying to do? We're trying to get our model to predict on the same type of data it was trained on. So let's go custom image transform is transforms.compose. And we're just going to, since our image is already of a tensor, let's do transforms.resize and we'll set the size to the same shape that our model was trained on, or the same size that is. So let's go from torch vision. We don't have to rewrite this, it's already imported, but I just want to highlight that we're using the transforms package. We'll run that. There we go, we've got a transform pipeline. Now let's see what happens when we transform our target image. Transform target image, what happens? Custom image transformed. I love printing the inputs and outputs of our different pipelines here. So let's pass our custom image that we've just imported. So custom image transform. Our custom image is, recall, of shape, quite large. We're going to pass it through our transformation pipeline and let's print out the shapes. Let's go original shape and then we'll go custom image dot shape and then we'll go print transformed shape is going to be custom image underscore transformed dot shape. Let's see the transformation. Oh, would you look at that? How good. We've gone from quite a large image to a transformed image here. So it's going to be squished and squashed a little. So that's what happens. Let's see what happens when we plot our transformed image. We've gone from 4,000 pixels on the height to 64, and we've gone from 3,000 pixels on the height to 64. So this is what our model is going to see. Let's go custom image transformed, and we're going to permute it to be 120. Okay, so quite pixelated. Do you see how this might affect the accuracy of our model? Because we've gone from custom image, is this going to, oh yeah, we need to plot.imshow. We've gone from this high definition image to an image that's of far lower quality here. And I can kind of see myself that this is still a pizza, but I know that it's a pizza. So just keep this in mind going forward, is that another way that we could potentially improve our model's performance if we increased the size of the training image data. So instead of 64, we might want to upgrade our model's capability to deal with images that are of 224, 224. So if we have a look at what this looks like, 224, 224. Wow, that looks a lot better than 64, 64. So that's something that you might want to try out later on, but we're going to stick in line with the CNN explainer model. How about we try to make another prediction? So since we've transformed our image to be the same size as the data our model was trained on, so with torch inference mode, let's go custom image pred equals model1 on custom image underscore transformed. Does it work now? Oh my goodness, still not working. Expected all tensors on the same device. Of course, that's what we forgot here. Let's go to device. Or actually, let's leave that error there. And we'll just copy this code down here. And let's put this custom image transform back on the right device and see if we finally get a prediction to happen with our model. Oh, we still get an error. Oh my goodness, what's going on here? Oh, we need to add a batch size to it. So I'm just going to write up here, this will error, no batch size, and this will error, image not on right device, and then let's try again. We need to add a batch size to our image. So if we look at custom image transformed dot shape, recall that our images that pass through our model had a batch dimension. So this is another place where we get shape mismatch issues. Is if our model, because what's going on in a neural network is a lot of tensor manipulation, if the dimensions don't line up, we want to perform matrix multiplication, and the rules, if we don't play to the rules, the matrix multiplication will fail. So let's fix this by adding a batch dimension. So we can do this by going a custom image transformed. Let's unsqueeze it on the first dimension and then check the shape. There we go. We add a single batch. So that's what we want to do when we make a prediction on a single custom image. We want to pass it to our model as an image or a batch of one sample. So let's finally see if this will work. Let's just not comment what it will do. This, or maybe we'll try anyway. This should work. Added a batch size. So do you see the steps we've been through so far? I'm just going to unsqueeze this. Unsqueeze on the 0th dimension to add a batch size. Oh, it didn't error. Oh my goodness. It didn't error. Have a look at that. Yes, that's what we want. We get a prediction logit because the raw outputs of our model. We get a logit value for each of our custom classes. So this could be pizza, this could be steak, and this could be sushi, depending on the order of our classes. Let's just have a look. Class to IDX. Did we not get that? Class names. Beautiful. So pizza, steak, sushi. We've still got a ways to go to convert this into that, but I just want to highlight what we've done. So note, to make a prediction on a custom image, we had to, and this is something you'll have to keep in mind for almost all of your custom data. It needs to be formatted in the same way that your model was trained on. So we had to load the image and turn it into a tensor. We had to make sure the image was the same data type as the model. So that was torch float 32. And then we had to make sure the image was the same shape as the data the model was trained on, which was 64, 64, 3 with a batch size. So that was 1, 3, 64, 64, and excuse me, this should actually be the other way around. This should be color channels first because we're dealing with PyTorch here. 64, and then finally we had to make sure the image was on the same device as our model. So they are three of the big ones that we've talked about so much. Same data type or data type mismatch will result in a bunch of issues. Shape mismatch will result in a bunch of issues, and device mismatch will also result in a bunch of issues. If you want these to be highlighted, they are in the Learn pytorch.io resource. We have putting things together. Where do we have it? Oh yeah, no, it's in the main takeaway section, sorry. Predicting on your own custom data with a trained model is possible as long as you format the data into a similar format to what the model was trained on. So make sure you take care of the 3 big PyTorch and deep learning errors: wrong data types, wrong data shapes, and wrong devices. Regardless of whether that's images or audio or text, these 3 will follow you around. So just keep them in mind. But now we've got some code to predict on custom images, but it's kind of all over the place. Like we've got about 10 coding cells here just to make a prediction on a custom image. How about we functionize this and see if it works on our pizza dad image? I'll see you in the next video. Welcome back. We're now well on our way to making custom predictions on our own custom image data. Let's keep pushing forward. In the last video, we finished off getting some raw model logits, so the raw outputs from our model. Now, let's see how we can convert these logits into prediction labels. Let's write some code. So convert logits to prediction labels, or let's go convert logits. Let's first convert them to prediction probabilities. So how do we do that? Let's go custom image pred probs equals torch.softmax to convert our custom image pred across the first dimension. So the first dimension of this tensor will be the inner brackets, of course. So just this little section here. Let's see what these look like. This will be prediction probabilities. Wonderful. So you'll notice that these are quite spread out. Now, this is not ideal. Ideally, we'd like our model to assign a fairly large prediction probability to the target class, the right target class, that is. However, since our model, when we trained it, isn't actually performing all that well, the prediction probabilities are quite spread out across all of the classes. But nonetheless, we're just highlighting what it's like to predict on custom data. So now let's convert the prediction probabilities to prediction labels. Now, you'll notice that we used softmax because why? We are working with multi-class classification data. And so we can get the custom image pred labels, or the integers, by taking the argmax of the prediction probabilities. Custom image pred probs across the first dimension as well. So let's go custom image pred labels. Let's see what they look like. 0. So the index here with the highest value is index number 0. And you'll notice that it's still on the CUDA device. So what would happen if we tried to index on our class names with the custom image pred labels? Or maybe that doesn't need to be a plural. Oh, there we go. We get pizza. But you might also have to change this to the CPU later on. Otherwise, you might run into some errors. So just beware of that. So you notice how we just put it to the CPU. So we get pizza, we got a correct prediction, but this is as good as guessing in my opinion, because these are kind of spread out. Ideally, this value would be higher, maybe something like 0.8 or above for our pizza dad image. But nonetheless, our model is getting 2 thumbs up, even on this 64 by 64 image. But that's a lot of code that we've written. Let's functionize it. So we can just pass in a file path and get a custom prediction from it. So putting custom image prediction together, let's go building a function. So we want the ideal outcome is, let's plot our image as well. Ideal outcome is a function where we plot or where we pass an image path to and have our model predict on that image and plot the image plus the prediction. So this is our ideal outcome, and I think I'm going to issue this as a challenge. So give that a go, put all of our code above together, and you'll just have to import the image, you'll have to process it and whatnot. I know I said we were going to build a function in this video, but we're going to save that to the next video. I'd like you to give that a go. So start from way back up here, import the image via TorchVision IO read image, format it using what we've done, change the data type, change the shape, change the device, and then plot the image with its prediction as the title. So give that a go, and we'll do it together in the next video. How'd you go? I just realized I had a typo in the previous cell, but that's all right. Did you give it a shot? Did you put together the custom image prediction in a function format? I'd love it if you did, but if not, that's okay. Let's keep going. Let's see what that might look like. And there are many different ways that you could do this, but here's one of the ways that I've thought of. So we want a function that's going to pred and plot a target image. We want it to take in a torch model. And so that's going to be ideally a trained model. We want it to also take in an image path, which will be of a string. It can take in a class names list so that we can index it and get the prediction label in string format. So let's put this as a list of strings. And by default, this can equal none, just in case we just wanted the prediction. It wants to take in a transform so that we can pass it in some form of transform to transform the image. And then it's going to take in a device, which will be by default the target device. So let's write a little doc string here. Makes a prediction on a target image with a trained model and plots the image and prediction. Beautiful. Now, what do we have to do first? Let's load in the image. Load in the image just like we did before with TorchVision. So target image equals torchvision.io.read image, and we'll go string on the image path, which will be the image path here, and we convert it to a string just in case it doesn't get passed in as a string. And then let's change it into type torch float 32, because we want to make sure that our custom image or our custom data is in the same type as what we trained our model on. So now let's divide the image pixel values by 255 to get them between 0 or to get them between 0, 1 as a range. So we can just do this by target image equals target image divided by 255. And we could also just do this in one step up here, 255, but I've just put it out there just to let you know that, hey, read image imports image data as between 0 and 255. So our model prefers numbers between 0 and 1, so let's just scale it there. Now, we want to transform our data if necessary. In our case, it is, but it won't always be. So we want this function to be pretty generic, pred and plot image. So if the transform exists, let's set the target image to the transform, or we'll pass it through the transform, that is. Wonderful. And the transform we're going to get from here. Now what's left to do? Well, let's make sure the model is on the target device. It might be by default, but if we're passing in a device parameter, we might as well make sure the model is there too. And now we can make a prediction. So let's turn on eval/inference mode and make a prediction with our model. So model, we'll call eval mode, and then with torch.inference mode, because we're making a prediction, we want to turn our model into inference mode or put it in inference mode context. Let's add an extra dimension to the image. Let's go target image. We could do this step above actually, but we're just going to do it here. I'm kind of remembering things on the fly here of what we need to do. We're adding let's write this down. This is the batch dimension. E.g. our model will predict on batches of 1x image. So we're just unsqueezing it to add an extra dimension at the 0th dimension space, just like we did in a previous video. Now let's make a prediction on the image with an extra dimension. Otherwise, if we don't have that extra dimension, we saw that we get a shape issue. So right down here, target image pred, and remember this is going to be the raw model outputs. raw logit outputs. We'll go target image pred, and yeah, I believe that's all we need for the prediction. Oh wait, there was one more thing. To device. Need to also make sure the target image is on the right device. Beautiful. So a fair few steps here, but nothing we can't handle. All we're really doing is replicating what we've done for batches of images, but we want to make sure that if someone passed any image to our pred and plot image function, that we've got functionality in here to handle that image. And do we get this? Oh, we want just target image to device. Did you catch that error? So let's keep going. Now let's convert the logits. Our model's raw logits. Let's convert those to prediction probabilities. This is so exciting. We're getting so close to making a function to predict on custom data. So we'll set this to target image pred probs, which is going to be torch.softmax. And we will pass in the target image pred here. We want to get the softmax of the first dimension. Now let's convert our prediction probabilities, which is what we get in the line above. We want to convert those to prediction labels. So let's get the target image pred labels equals torch.argmax. We want to get the argmax of, or in other words, the index, which is the maximum value from the pred probs of the first dimension as well. Now, what should we return here? Well, we don't really need to return anything. We want to create a plot. So let's plot the image alongside the prediction and prediction probability. Beautiful. So plot.imshow, what are we going to pass in here? We're going to pass in here our target image. Now we have to squeeze this, I believe, because we've added an extra dimension up here. So we'll squeeze it to remove that batch size. And then we still have to permute it because matplotlib likes images in the format color channels last, 1 to 0. So remove batch dimension and rearrange shape to be HWC, that is, color channels last. Now, if the class names parameter exists, so we've passed in a list of class names, this function is really just replicating everything we've done in the past 10 cells, by the way. So right back up here, we're replicating all of this stuff in one function. So pretty large function, but once we've written it, we can pass in our images as much as we like. So if class names exist, let's set the title to showcase that class name. So the pred is going to be class names. Let's index on that, pred image or target image pred label. And this is where we'll have to put it to the CPU, because if we're using a title with matplotlib, matplotlib cannot handle things that are on the GPU. This is why we have to put it to the CPU. And then I believe that should be enough for that. Let's add a little line in here so that we can have it, oh, I've missed something, an outside bracket there. Wonderful. Let's add the prediction probability, because that's always fun to see. So we want target image pred probs, and we want to get the maximum pred prob from that, and we'll also put that on the CPU. And I think we might get this to 3 decimal places. Now this is saying, oh, pred labels, we don't need that. We need just non-plural. Beautiful. Now, if the class names doesn't exist, let's just set the title equal to f string. We'll go pred target image pred label. Is Google Colab still telling me this is wrong? Target image pred label. Oh no, we've still got the same thing. It just hasn't caught up with me yet. I'm coding a bit fast here. And then we'll pass in the prob, which will be just the same as above. I could even copy this in. Beautiful. And let's now set the title to the title, and we will turn the axes off. PLT axes false. Fair bit of code there, but this is going to be a super exciting moment. Let's see what this looks like when we pass it in a target image and a target model, some class names, and a transform. Are you ready? We've got our transform ready, by the way. It's back up here. Custom image transform. It's just going to resize our image. So let's see. Oh, this file was updated remotely or in another tab. Sometimes this happens, and usually Google Colab sorts itself out, but that's all right. Doesn't affect our code for now. Pred on our custom image. Are you ready? Save failed. Would you like to override? Yes, I would. So you might see that in Google Colab. Usually it fixes itself. There we go. Save successfully. Pred and plot image. I was going to say, Google Colab, don't fail me now. We're about to predict on our own custom data. Using a model trained on our own custom data. Image path, let's pass in custom image path, which is going to be the path to our pizza dad image. Let's go class names equals class names, which is pizza, steak, and sushi. We'll pass in our transform to convert our image to the right shape and size. Custom image transform. And then finally, the target device is going to be device. Are you ready? Let's make a prediction on custom data. One of my favorite things, one of the most fun things to do when building deep learning models. 3, 2, 1. How did it go? Oh no, what did we get wrong? CPU. Okay, so close, but yet so far. Has no attribute CPU. Oh, maybe we need to put this to CPU. That's where I got the square bracket wrong. So that's what we needed to change. We needed to, because this is going to be potentially on the GPU, targ image pred label, we need to put it on the CPU. We need to do that. Why? Because this is going to be the title of our matplotlib plot, and matplotlib doesn't interface too well with data on a GPU. Let's try it again. 3, 2, 1, running. Woohoo! Look at that. Prediction on a custom image, and it gets it right. 2 thumbs up. I didn't plan this. Our model is performing actually quite poorly, so this is as good as a guess to me. You might want to try this on your own image, and in fact, if you do, please share it with me. I would love to see it. But you could potentially try this with another model, see what happens. Steak. Okay, there we go. So even though model 1 performs worse quantitatively, it performs better qualitatively. So that's the power of visualize, visualize, visualize. And if we use model 0, also, which isn't performing too well, it gets it wrong with a prediction probability of 0.368, which isn't too high either. So we've talked about a couple of different ways to improve our models. Now we've even got a way to make predictions on our own custom images. So give that a shot. I'd love to see your custom predictions. Upload an image here if you want, or download it into Google Colab using code that we've used before. But we've come a fairly long way. I feel like we've covered enough for custom data sets. Let's summarize what we've covered in the next video. And I've got a bunch of exercises and extra curriculum for you. So this is exciting stuff. I'll see you in the next video. In the last video, we did the very exciting thing of making a prediction on our own custom image. Although it's quite pixelated, and although our model's performance quantitatively didn't turn out to be too good, qualitatively, it happened to work out. But of course, there are a fair few ways that we could improve our model's performance. But the main takeaway here is that we had to do a bunch of pre-processing to make sure our custom image was in the same format as what our model expected. And this is quite a lot of what I do behind the scenes for Nutrify. If you upload an image here, it gets pre-processed in a similar way to go through an image classification model to output a label like this. So let's get out of this. To summarize, I've got a colorful slide here, but we've already covered this. Predicting on custom data. These are 3 things to make sure of regardless of whether you're using images, text, or audio. Make sure your data is in the right data type. In our case, it was torch float 32. Make sure your data is on the same device as the model. So we had to put our custom image to the GPU, which was where our model also lived. And then we had to make sure our data was in the correct shape. So the original shape was 64-64-3. Actually, this should be reversed because it was color channels first, but the same principle remains here. We had to add a batch dimension and rearrange if we needed. So in our case, we used images of this shape, batches first, Color channels first, height, width. But depending on your problem will depend on your shape, depending on the device you're using will depend on where your data and your model lives, and depending on the data type you're using will depend on what you're using for Torch Float 32 or something else. So let's summarize. If we go here, main takeaways, you can read through these, but some of the big ones are PyTorch has many built-in functions to deal with all kinds of data, from vision to text to audio to recommendation systems. So if we look at the PyTorch docs, you're going to become very familiar with these over time. We've got Torch audio data, Torch text, Torch vision is what we practiced with. And we've got a whole bunch of things here for transforming and augmenting images, data sets, utilities, operators, and Torch data is currently in beta, but this is just something to be aware of later on. So it's a prototype library right now, but by the time you watch this, it might be available. But it's another way of loading data. So just be aware of this for later on. And if we come back to up here, if PyTorch built-in data loading functions don't suit your requirements, you can write your own custom dataset classes by subclassing torch.utils.data.dataset. And we saw that way back up here in option number 2. Option 2, here we go. Loading image data with a custom dataset. We wrote plenty of code to do that. And then a lot of machine learning is dealing with the balance between overfitting and underfitting. We've got a whole section in the book here to check out what an ideal loss curve should look like and how to deal with overfitting, how to deal with underfitting. It is a fine line. So much of the research in machine learning is actually dedicated towards this balance. And then 3 big things for being aware of when you're predicting on your own custom data: wrong data types, wrong data shapes, and wrong devices. This will follow you around, as I said, and we saw that in practice to get our own custom image ready for a trained model. Now, we have some exercises here. If you'd like the link to it, you can go to learnpytorch.io, section number 4, exercises, and of course, extra curriculum. A lot of the things I've mentioned throughout the course that'd be a good resource to check out contained in here. But the exercises, this is your time to shine, your time to practice. Let's go back to this notebook, scroll right down to the bottom. Look how much code we've written. Goodness me. Exercises. For all exercises and extra curriculum, see here. Turn that into Markdown. Wonderful. And so if we go in here, you've got a couple of resources. There's an exercise template notebook for number 4 and example solutions for notebook number 4, which is what we're working on now. So of course, I'd encourage you to go through the PyTorch custom datasets exercises template first. Try to fill out all of the code here on your own. So we've got some questions here, we've got some dummy code, we've got some comments. So give that a go. Go through this, use this book resource to reference, use all the code we've written, use the documentation, whatever you want, but try to go through this on your own. And then if you get stuck somewhere, you can look at an example solution that I created, which is here, PyTorch custom datasets exercise solutions, and just be aware that this is just one way of doing things. It's not necessarily the best, it's just a way to reference what you're writing to what I would do. And there's actually now live walkthroughs of the solutions, errors and all, on YouTube. So if you go to this video, I'm just going to mute. So this is me live streaming the whole thing, writing a bunch of PyTorch code. If you just keep going through all of that, you'll see me writing all of the solutions, running into errors, trying different things, etc., etc. But that's on YouTube. You can check that out on your own time. But I feel like we've covered enough. Exercises. Oh, by the way, this is in the extras exercises tab of the PyTorch Deep Learning repo. So extras, exercises and solutions are contained in there. Far out. We've covered a lot. Look at all that. So that has been PyTorch Custom Datasets. I will see you in the next section. Holy smokes. That was a lot of PyTorch code. But if you're still hungry for more, there is 5 more chapters available at learnpytorch.io, which cover transfer learning, my favorite topic, PyTorch model experiment tracking, PyTorch paper replicating, and PyTorch model deployment. How do you get your model into the hands of others? And if you like to learn in this video style, the videos for those chapters are available at zerotomastery.io. But otherwise, happy machine learning, and I'll see you next time.